Okay, here's an example on the video that I promised you of an example forming a solid by taking geometric cross sections of some familiar shapes. So squares, semicircles, and variations of that. We're going to look at a region that's bounded by the curves y equals radical x and y equals negative radical x, and then the line x equals 4. So I'm going to go ahead and do a quick sketch of this. So y equals radical x is going to be something like this. Negative radical x, let's try again with that one. Make it look somewhat the same. There we go. And then x equals 4. I suppose I'll put 1, 2, 3, 4. Something like this. So what that is that is the base of my solid. Think of it as coming up, three-dimensionally, it's coming up, rising off of the paper or the screen that you're looking at. And I've got, let's just start with square cross section. So to try to draw it again is super hard, but I'm going to try to draw it as kind of like a side view. So here's me kind of looking at a side view of what I just drew. And my squares are coming off of there. So for this right here, I have a square. And then for a space here, I've got a bigger square because my base is bigger, so I'm higher. And then I've got a little square over here. And little squares leading to this. And then I've got bigger squares behind this. And then we end up with this section that kind of has these ridges as we go. So that's what I'm getting, is something like that. Now, you don't really need to be able to picture it as the good part, because really what we're going to do is we are going to use the same formula every single time. So here's what it's going to look like. You might want to refer to your formulas. My volume is going to be the integral of from a to b, and we'll figure that out in a second, of my first function, or my top function, minus my bottom function, squaring that quantity, because I'm doing the area of a square. So I'm really doing base times height, where f of x minus g of x is my base, and multiplying that by dx. So just to do a quick reference to my picture, my f of x minus g of x is the base of any one of these squares, because that's really the distance between my two curves. So go back to area between the two curves. We found out the area by taking top curve minus bottom curve, and at any point that gave me the distance between them, which is a corresponding base or side of my square. So in this case, my top curve is my radical x, and my bottom curve is my negative radical x. So I'm going to do radical x minus a negative radical x. Don't forget you have to square that quantity, times dx. And my limits of integration, I should go ahead and put those on. If you're looking at this, that really comes from my picture, and what I know are 0 to 4. On my x-axis, I start at 0, and then I go to 4 over here. So 0 to 4 for my limits of integration. And now I'm just in calculus mode. That was the setup. And not actually too bad, because this simplifies. So from 0 to 4, radical x minus a negative radical x becomes plus a positive, which is 2 radical x. I'm squaring that quantity. Notice I'm using parentheses so they don't forget something, because I'm going to have to square the 2 and square the radical x. So 2 becomes 4. Radical x squared is x. And that's about the simplest integral that we've seen in a long time. So let's go ahead and integrate. And once I integrate, I'm going to get 4x squared over 2. Can cancel that. So I've got 2x squared, evaluating that from 0 to 4. So that's giving me, let's go ahead and put that in. So that's giving me 2 times 4 squared is 16. Nope, my 2 canceled out. That's gone. So I've got 2 times 16 minus 2 times 0, which is just a 0. So I've got 32 units. Whoops, units cubed, because I'm doing volume. Okay, so what did we just found? We found really the area of, there it is, that green guy. area of my entire green solid that I'm creating by my squares that I have. So that's what I've got right here. Now, the good news about these problems and what I told you when I said that these were really easier than what we'd been doing is that we're going to use a variation of this for the other one. So if you look back at your notes and what you have for your formulas for the volume of the solid, if we have equilateral triangles or semicircles that are making this region instead of squares, the only difference is a constant out front. So I'm just going to do one other one. I'm going to move all of this up here, and I'm going to say, page, let's suppose that I'm doing cross sections that are semicircles. So my formula is now volume is equal to pi over 8. Look back at your notes for how we got that. Times the integral from 0 to 4 of f of x minus g of x, which is radical x minus a negative radical x quantity squared dx. And then I'm going to say, wait a second, this entire thing we already calculated a little bit ago. We calculated this to be 32. So you don't need to redo it all. You're just going to multiply times pi over 8. So 32, and we have a pi over 8 in front, is going to equal 32 pi over 8, divide by 4, or divide 32 by 8, and I'm going to get 4 pi units cubed. That would be part B, which was the volume when cross sections are semicircles. I think you get the idea from there. So change it accordingly to what you have to multiply by out front, but certainly use that to help you so you don't take so much time to do it every single time. You don't need to do it different. Just going to point out that when you get to number 2, it is intended to be a calculator problem. So I would set up the integral, something like what we have right here, write that down, and then go ahead and put it in your calculator. If you do this part separately, then you'll have that number and you can multiply it by the corresponding constant that you pulled out front to get your remaining answers as you work through that one.